Okay, so this is the start of a new topic, electricity at home. And this first lesson we're going to be looking at alternating currents, direct current and flux. So to start with, we're going to compare direct current to alternating current. So I've got two graphs here of voltage against time. So voltage on my y-axis and time along my x-axis. So the direct current graph is on the left and the alternating current is on the right. And I'd like you to have a think about the differences in the changes in voltage over time for AC compared to DC by using these graphs. How would you describe the voltage for a direct current over time, and how would you describe it for the alternating current over time? So direct current, this is in circuits using batteries. So batteries have a fixed positive and a fixed negative terminal. And so when we use them in circuits, this means that our electrons will travel in a particular direction as they're repelled from the negative terminal of the battery, and so they travel away from that negative terminal. So our current is the rate of flow of charge, and in this case our charge is electrons, and so our current is looking at the rate of flow of those moving electrons. So if our electrons are moving in one direction, then the current will also only be moving in one direction. This diagram on the right, this is just to show you that actually our direction of current is the opposite direction of our electron flow. And this is because we have our current as a positive direction, whereas our electrons, because they're negative, then they're opposite to that conventional direction of current. Alternating current, this is from our mains electricity, so electricity that's supplied to us from power stations. Now this doesn't have a fixed voltage, it rapidly changes from positive to negative, as you saw in that graph on the first slide. So in circuits, our electrons will still always be travelling away from the negative terminal, as electrons are negatively charged. However, as our voltage is changing, this means that the electrons are going to be alternating their direction of travel depending on which voltage is being applied. So this is an example. We've got two circuits here. Notice instead of our normal symbol of a cell battery, we've got like an S shape, and this looks a lot like the graph that we saw on the first page for AC, and this is to symbolise that it's an alternating current being applied rather than the direct current that batteries supply. So you'll notice that here it's positive on the top, but on this one it's negative on the top. And we've got our current given symbol of I that is then in different directions depending on the polarity of our power supply. So the current is going to be repeatedly reversing its direction whilst AC current is being supplied. So our main circuits, we have two key variables that we need to learn. So our frequency, which is the number of waves per second measured in hertz. We'll look more at that when we do our waves topic. But in terms of our alternating currents, it's the number of those alterations is 50 hertz, and the voltage that is supplied by the mains power supply is 230 volts. From the diagram below, I'd like you to list the components that make up the national grid. This shows our step-up transformer converting our potential difference from 25,000 kilovolts to 132 kilovolts or more, and then our step down, reducing that to the 230 volts which are supplied to our homes. This is a map of where we are and the power stations that are near us. Notice there's one that is a nuclear power station all the way along the coast. This is what a substation looks like, and so they transform the electricity from the high voltage that's travelling along the cables overhead to the 230 volts that is supplied to our homes. So our national grid is a network of cables and transformers that is used to supply electricity from our power stations. So you'll see here that the power station, it starts off with a very high potential difference of 25,000 volts. They then step this up to 400,000 volts for when it's travelling along the overhead cables. This then gets stepped down to 132,000 watts or 25,000 watts, depending on what it's then going to be used for. But before it gets to our homes, it then has to be stepped down again to that 230 volts. This diagram does put it at 240 volts, however our ACDC specification has it as 230 volts, so that is the one that we need to be learning. So transformers, this is new to us, and what they're doing is they're changing the size of the alternating potential difference. So a step-up transformer will increase the size, and we use this from our power station to transfer it to the national grid. And this is advantageous to us in that it means that we can then apply less current, and so we get less lost through resistance of heating in the cables. So this means it's more efficient for us to have that large potential difference. As our voltage increases, then our current decreases if we look at that I equals PV, P over V equation. Our step down transformers, these are decreasing the size of your alternating potential difference, and this is in order for it to be transferred to our homes, offices and factories. Note that our factories actually have a much higher potential difference applied due to the higher amount that they need compared to the equipment and appliances that we use in our homes. So I'd like you to order these into the correct order and also explain why the transformers are needed in the national grid. So why is it beneficial to transmit electricity through cables to our homes at a high potential difference? So we talked about this, so this was that our electricity is transmitted at a high potential difference, resulting in a lower current being used, and so less energy is transferred to the surroundings due to heating of the cables. And remember that heating of the cables is as a result of the resistance in the wires. And why is it beneficial for our potential difference to be reduced before it is supplied to our homes? And that's because it's going to be making it safer for us to use at our homes. Our electrical cables that are overhead or overground. So there are advantages of each type of cable. So our overhead ones are cheaper and easier to repair. As they're high above the ground, they're less easily damaged. It's easier to cross geographical features such as rivers with these overhead cables. They will also cool relatively quickly. However, underground cables are hidden from sight, so they're not going to be spoiling the landscape. And also we can avoid any potential health problems caused by electric and magnetic fields. So our main supply is delivered through cables which are made up of two wires, so the live wire and the neutral wire. So in every main circuit there's a live wire and a neutral wire. It's the live wire that is particularly dangerous, as it's this wire which has its potential difference repeatedly changing, and so it is alternately positive and negative at every cycle, and it's going to be at quite a high voltage on average. Our neutral wire, however, as the term neutral indicates to us, it has a voltage close as close to zero as possible, and this is because it's earthed at the local substation, and so that allows it to have a zero potential difference. In our plugs, as well as the live and main wire, we also have an earth wire in some appliances. Now, this earth wire is connected to the ground and would normally be at 0 volts, as it only carries a current if there is a fault. What I'd like you to do is to label this diagram. So things to label are the fuse, the live wire, the earth wire, the neutral wire, the cable grip. Earthing is where we're connecting the case of our metal appliance to the ground through the earth wire. So this is in order for if our live wire broke and ended up touching the metal case, the earth wire is going to stop this metal case from becoming live and therefore protecting us from getting electrocuted if we were to touch the metal case. 3-pin plugs, so this is the common plugs that we use in the UK, and what I'm going to show you is what they look like on the inside, and also highlight the fact that our earth pin is longer to ensure that when we are plugging in our plugs, it's earthed before the live wires are connected. Okay, so this is the plug for my desk lamp. Now, it's quite hard to see under the visualizer. However, if you find one at home, you'll be able to see that actually there's a lot of inscribings on the outer casing of this. So there we've got the E at the top for the earth, L on the left for the live, and the N on the right for the neutral. You've also got a opening by the fuses, and this tells you the maximum voltage that should be applied. So this part here is the cable grip, and this is to ensure that it doesn't get pulled out of the plug. What we see here is that this doesn't actually have an earth cable. This is quite surprising to me because this is metal. However, it must mean that it's doubly insulated on the inside. But our fuse here, if we take it out, as you can see, it's connected up to our brown live wire, and here you can see it's a 3 amp fuse. And again, on the inside we have the inscriptions, so E at the top for the earth, and then we should have an N, which is hidden by that blue wire, but you can hopefully see the start of the N, and then there's an L under the brown. On the side here you can hopefully see a hole underneath where the screw is, and that is where your earth wire would get threaded into if it was to have one. Also, just use this opportunity to show that height difference between our earth and our neutral and live pins, so that it's automatically earthed as it goes into the socket. So having now checked the bottom of this product, this 2 squares within each other, this tells us that it is doubly insulated, and that's why there isn't an earth wire in this. The picture on the right also just shows you what the sockets look like that you're plugging them into. So you've got your live and neutral wires connected from the main supply, and then also that earthing process that's going on. So fuses, they are thin pieces of wire, and when we apply a current that is too high for it, then this causes the wire to melt. So this effectively breaks the circuit, so we can say that the fuse has blown. and we rate them in terms of the current that causes them to melt. The three different ratings that we have is a 3 amp, a 5 amp and a 13 amp. So the 3 amp would require a current of 3 amps in order to melt it, the 5 amp requires a current of 5 amps or more to melt it, and the 13 amp would require a current of 13 amps or more to melt it. So it's important that the fuse that we are choosing is greater than the current in which we require, but also it's the nearest one to the current we require. So this activity is now looking at us choosing the correct fuse by calculating the current. So in order to do this, you need to use the equation current equals power divided by potential difference. So just dividing the numbers, say 2600 divided by 230, and in fact, because it's our main supply, then it's going to be 230 each time. We then need to look at the current and choose the correct size out of the 3 amp, 5 amp and 13 amps that we should use in order to protect us and the appliance. In the diagram here, we've got the information plate that's on the bottom of an electric wallpaper steamer. So it's telling us 230 volts, 50 hertz, and a power of 2.3 kilowatts, so 2,300 watts. Again, I've given you the equation, but I'd like you to calculate the current used by the steamer, so showing your workings by using that equation, and then decide which of the fuses should be used inside the plug of the steamer. Some questions for you to have a look at. You might want to research some of this using BBC Bitesize, as we haven't gone through all of these, particularly the materials that we use. Why are the pins made of brass and not copper? Thinking about the properties of brass compared to copper. Why is copper used for wires? Again, thinking about the properties of copper, thinking about what you just established with brass. Why the plug casing is plastic. Why Hoovers don't have an earth wire. Why the cables connecting sockets are thicker than those used in the lighting. Thinking in terms of what affects resistance. I always think about resistance of a wire in terms of your ability to go down a corridor. So if you've got a thicker or wider corridor, is it easier or harder for you to get to your class? And then why would you not use a 3 amp fuse for an appliance which has a current of 3 amps running through it? What causes a short circuit? And then finally, why should you never touch the live wire? Once you have done these, I've then done an escape to virtual classroom, requiring the knowledge that you will have picked up through this lesson in order to help some scientists escape from their lab.